One of the most, I don't know, mind-blowing ideas in quantum mechanics, the de Broglie wavelength.
Yeah,
You know how, like, in the everyday world, we think of waves and particles as, like, totally separate things?
right.
Well, get ready because we're going to explore this concept that says everything, even like a baseball, has a wavelength.
It's true.
It's crazy, right?
Yeah, it really challenges how we, think about reality on a day-to-day basis. I think
Yeah.
the thing that is so fascinating about the de Broglie wavelength is it kind of creates a bridge between the macroscopic world, the stuff that we see and feel, and the quantum world, which is so different.
Totally. So just to make sure everyone's with us, what is the de Broglie wavelength?
Okay, so in the simplest terms, it's the idea that every moving particle, I mean, everything, no matter how big or how small, has a wave that is associated with it.
So like a baseball flying through the air is like waving.
It's not a wave in the way that we think of like waves in the ocean. It's more of a probability wave. And it describes the likelihood of finding that particle at a certain point in space. And the wavelength of that probability wave is what de Broglie figured out.
Okay, so like there's a formula.
Yeah, there is. It's actually
Mhm.
pretty elegant. The wavelength equals Planck's constant divided by the particle's momentum.
Okay, so break that down for me.
Okay.
Let's stick with the baseball.
Yeah.
Like it's got a lot of momentum, right?
It does, yeah.
Mm.
A baseball has a lot of mass, and it's moving fast, so it has high momentum. And since wavelength is inversely proportional to momentum, a baseball's wavelength ends up being incredibly tiny. Like, we can't even detect it.
Yeah. So something with a lot of momentum has a tiny wavelength.
Right.
What about something super small like an electron?
Now, things get interesting.
Yeah.
An electron has such a tiny mass that even when it's moving really fast, its momentum is still relatively small.
Mm.
And that means that its de Broglie wavelength is actually much larger. Like, we can actually observe it.
Wait, so we can like see the wave nature of an electron?
Not with our eyes,
Yeah.
but we can see its effects.
Okay.
And one of the key pieces of evidence that sort of validated de Broglie's hypothesis is the Davison-Germer experiment.
Oh, yeah. What happened there?
So imagine shooting a beam of electrons at a crystal, kind of like, shining a light through a narrow slit. If electrons were just particles, you'd expect them to like pass straight through or bounce off in a predictable way.
Makes sense.
But that's not what happened.
Oh.
Instead, what they observed was an interference pattern on the other side of the crystal.
Like ripples.
Yeah, like ripples in a pond. And this pattern is a, classic sign of wave behavior. And it was a huge surprise to physicists at the time.
Yeah, so the electrons were acting like waves
It
and
was,
interfering with each other.
yeah, and that's where de Broglie's genius comes in, right? He said,
Mhm.
hey, this wave-like behavior, it's not just for light, it's for all matter.
That's a pretty radical idea. I'm starting to see why this de Broglie guy was such a game changer.
Yeah, his work was really, really important for the development of quantum mechanics. I mean, it challenged the very core of classical physics
Yeah.
and really paved the way for us to understand the universe in a totally new way.
So de Broglie drops this bombshell about matter having wave-like properties. So, like, what happened next?
Well, so imagine you're dropping a pebble in a still pond, right? De Broglie's idea was that pebble and the ripples that it created spread out and impacted everything.
Okay.
It led to other really, really groundbreaking ideas like Schrodinger's equation,
Right.
which is a mathematical framework for how these matter waves evolve over time.
Okay. I've heard of Schrodinger's cat,
Right.
but the equation, yeah, a little over my head.
Don't worry, the math can get pretty intense,
Uh-huh.
but
Okay.
the important takeaway is that Schrodinger's equation builds upon de Broglie's concept,
Okay.
and it really solidifies that the behavior of these particles is totally linked to their wave nature.
So de Broglie's idea wasn't just some, like, abstract concept. It was actually like a springboard for a whole new way of thinking about physics.
Exactly. But it gets even deeper than that, right? One of the most profound consequences is something that you've probably heard of, Heisenberg's uncertainty principle.
Oh, yeah, the uncertainty principle. It's like the universe has limits on what we can know, right?
Exactly. Heisenberg realized that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It's almost as if, like, when you measure one of those properties, it, like, blurs the other one.
So you can't, like, pinpoint exactly where a particle is and how it's moving at the same time.
Right, and here's the key connection. Heisenberg's uncertainty principle is a direct consequence of the wave nature of matter that de Broglie described.
Wow.
It's not like our tools are limited. It's actually built into how reality works.
Hold on, I need a second to wrap my head around that.
It's pretty wild.
The very act of trying to measure a particle changes what we can know about it.
It is strange, but that's the quantum world for you. Yeah. And as we'll keep exploring, this uncertainty, this wave-like fuzziness, leads to some really bizarre phenomena, like the ability of particles to tunnel through barriers.
Oh, okay. Yeah.
But that's a story for our next dive.
Yeah, all right. Okay, yeah. I've had a minute to think about that last point. The whole idea that just trying to measure something in the quantum world, like, changes it.
Yeah.
Pretty wild stuff. But where do we go from there? What other, I don't know, weirdness does de Broglie's wavelength lead to?
Well, remember how we were talking about particles acting like waves? That leads us to a truly bizarre phenomenon. It's called quantum tunneling.
Tunneling. Okay,
Yeah.
so like an electron can just like teleport through a wall or something. That sounds like, I don't know, Star Trek or something.
Yeah, it sounds pretty crazy.
Yeah.
But it's a very real consequence of particles' wave nature. Think about it this way. In the quantum world, particles, they're described by these probability waves, right? And these waves, they can spread out, and even if part of the wave hits a barrier, a tiny piece of it can kind of seep through to the other side.
So even if it's like statistically improbable, there's still a chance that a part of the wave, and therefore the particle, can exist on the other side of a barrier.
Exactly. And that's the essence of quantum tunneling. It's not like it's breaking through the barrier. It's more like it's finding a way to exist on the other side because its wave function extends beyond the barrier.
Okay, I'm starting to see how this is like so different than how we think about physics in the everyday world, like classical physics.
Right.
So does this tunneling thing, does it actually happen in the real world, or is it just like a theoretical thing?
No, it's very real. And it's actually more important than you might think. Quantum tunneling is responsible for all sorts of phenomena. I mean, things like nuclear fusion in stars, even the way that transistors work in our electronics.
Oh, wow.
It's really important. Without it, our universe would be a completely different place.
Yeah, that's pretty amazing. I mean, it's crazy how something that sounds so weird is actually like fundamental to how our world works.
Yeah, it really shows the power of looking beyond our everyday assumptions and embracing the strangeness of quantum mechanics. But, tunneling is not the only mind-blowing consequence of de Broglie's work. It also paved the way for a completely different way of thinking about particles and fields. And it's this theory called quantum field theory, or QFT.
Yeah, QFT, I've heard physicists talk about that.
Yeah.
Always seemed a bit intimidating, to be honest.
I mean, it's definitely a leap from our everyday experience, but it can be pretty elegant once you get the hang of it. So imagine, instead of thinking of particles as tiny little solid objects, we think of them as, like excitations in these invisible fields that permeate all of space.
Okay, so instead of picturing an electron as like a tiny ball, I should think of it as like a ripple in some sort of electron field.
Yeah, that's the basic idea. And just as like waves in a pond have a certain wavelength and a frequency, these excitations in the quantum field, they also have wave-like properties,
Right.
including the de Broglie wavelength.
Okay, so de Broglie's idea isn't just about individual particles, it's actually like built into these quantum fields.
It is.
That's pretty wild.
It's a really profound way of looking at reality.
Yeah.
These fields are the fundamental building blocks of the universe.
Yeah.
And de Broglie's concept of the matter wave is really essential for understanding how they behave and interact.
Okay, this is starting to feel like I don't know, peeling back layers of an onion or something, just like more and more complexity.
Yeah.
But if everything is made of these like interacting fields, how do different types of particles even exist? Like how does the universe know to make an electron versus a photon?
It's a great question. The answer lies in the specific characteristics of each field. You see, each field has certain properties that determine what kind of particle it creates. It's like each field has its own set of rules that dictate how it behaves and how its excitations show up as particles.
So it's like a cosmic recipe book. This field makes electrons, that field makes photons, and so on.
Yeah, you got it.
But how does this all connect back to, the de Broglie wavelength? I'm starting to see how his work was so foundational, but I'm trying to like keep track of all the connections here.
Well, remember how we talked about the de Broglie wavelength being linked to a particle's momentum? That relationship plays a really crucial role in how these fields behave and interact.
Okay, yeah, remind me how that works again.
So a particle's momentum is related to its energy and how it's moving through space. And since de Broglie wavelength is inversely proportional to that momentum, it basically sets a limit on how tightly a particle can be localized, in space.
So the bigger the wavelength, wavelength, the less we can, like, pinpoint the particle's exact location. That sounds kind of like the uncertainty principle again.
Exactly. You're
Yeah.
getting it.
Yeah.
The uncertainty principle and the de Broglie wavelength, they're two sides of the same coin. They both come from the wave nature of matter, and they have these huge consequences for how particles behave, both individually and collectively.
Okay, so I'm starting to see the bigger picture now. De Broglie's work wasn't just about, like, calculating some abstract wavelength.
Right.
It was really about uncovering, a fundamental truth about the nature of matter itself.
Precisely. And as we go even deeper into the quantum world, we'll discover that the de Broglie wavelength is so much more than just a curious property. It's really a key to understanding so many things, from how atoms form to these crazy states of matter like Bose-Einstein condensates.
Bose-Einstein condensates. Okay, that's a new one for me. Are those connected to de Broglie wavelength too?
They are. You're a perfect example of how, the wave nature of matter can lead to some really mind-blowing phenomena. But I think that's a story for our next dive. I think we've covered a lot of ground already.
Yeah, we have.
And I think we need a minute to let it all sink in.
All right, I'm back and ready to, hear more about these Bose-Einstein condensates.
Yeah,
I gotta say, it sounds like, I don't know, something out of Star Trek.
it kind of does.
Yeah, but what are they? And, like, how do they connect back to all this stuff about, de Broglie and the wave nature of matter?
They're definitely a mind-bending concept.
Okay.
And a perfect example of how quantum mechanics leads to these states of matter that we wouldn't even imagine in our classical world.
Okay, well, what makes them so special?
Okay, so imagine a group of particles, like atoms, and they're cooled down to almost absolute zero,
Okay.
like the lowest temperature possible.
Yeah.
At these really, really low temperatures, something amazing happens.
So I'm picturing atoms, like, slowing down to a standstill.
That's part of it. But here's where the quantum weirdness comes in. Remember how de Broglie said particles have wave-like properties?
Yeah.
Well, as the atoms get colder and colder, their de Broglie wavelengths, they start to overlap
Okay.
and become really significant.
So it's like their individual waves are kind of merging into this one giant wave.
Exactly. And at this super low temperature, all of the atoms basically condense into a single quantum state and act like one giant superatom.
Okay.
This is a Bose-Einstein condensate, or BEC.
Wow. Okay. So instead of all these atoms bouncing around, they all become part of this, like, one unified thing.
That's a great way to put it, yeah.
Okay.
It's like their individual identities get blurry and they all act together, governed by one wave function.
So it's like a quantum chorus or something, all singing the same note.
I like that.
Yeah, but what makes that even possible?
It all comes down to the fact that these atoms are bosons. And a boson is a type of particle that, well, they don't mind sharing the same quantum state.
Okay.
Remember we talked about fermions?
Yeah, like electrons?
Right, like electrons, and they need their own space.
Yeah.
Well, bosons are the opposite. They're like the social butterflies of the quantum world.
Right. Yeah, it's all connecting now.
Yeah.
So because they're cool with, sharing the same state, when you cool them down enough, their wavelengths overlap, and boom, you get a BEC.
You got it.
It's crazy how de Broglie's idea about the wave nature of matter, like, underpins all of this.
It really is. And
Yeah.
BECs have some incredible properties. Like, they can be superfluid, which means they flow without any resistance.
Okay.
And they can be used to create these super precise atomic clocks.
Okay, this is mind-blowing. I mean, it just seems like the deeper we go into the quantum world, the weirder and more amazing it gets.
It really does.
But, we've been talking about all these, like, implications of de Broglie's work, the uncertainty principle, tunneling, BECs. Like, does this mean that we need to rethink reality itself?
I mean, that's a huge question. And it's one that physicists and philosophers, they've been wrestling with for, decades.
Yeah.
I think it's clear that the world, at the quantum level, doesn't behave according to the rules of classical physics that we're used to.
So is our everyday experience, like, an illusion then? Are we all just, like, walking, talking bundles of quantum weirdness?
I don't think it's that our everyday experience is an illusion.
Okay.
It's more that it's a very specific view,
Okay.
a macroscopic view of a universe that operates by different rules at the subatomic level. Think of it this way. Like, water waves are governed by fluid dynamics, right?
Yeah.
But if you zoom way in to the level of individual water molecules, those laws don't really apply anymore.
Okay, yeah, I see what you're saying. It's
Yeah.
like we're just seeing this, like, simplified, zoomed out version of a way more complex reality.
Exactly.
So does this mean, like, our intuition about the world is totally wrong?
I don't think so. I think our classical intuition is still very useful for navigating our everyday world.
Okay.
But it's good to remember that it's just an approximation. And when we get down to the quantum realm, we have to be willing to let go of some of those assumptions and really embrace a new way of thinking.
So what you're saying is the universe is even more, like, amazing and mysterious than we ever thought.
I think so. And, the de Broglie's idea about the matter wave, that was a key that really unlocked this hidden world.
Yeah.
This place where particles can be waves, uncertainty is just part of how things work, and even something like a baseball has a bit of quantum strangeness to it.
This has been a wild ride, this deep dive.
It has.
I mean, we've covered so much from, like, the very basics of de Broglie's idea to these, like, mind-blowing implications for, I don't know, for everything.
It's been great exploring all this with you.
Yeah.
And remember, the quantum world is full of mysteries waiting to be uncovered.
Yeah.
So keep that sense of wonder alive and never stop asking questions.
Well said, yeah. Thanks for joining us on this deep dive into the de Broglie wavelength.
My pleasure.
We hope you've come away with, I don't know, like, a new appreciation for the strangeness and the beauty of the quantum universe.
Yeah.
Until next time, keep exploring.